Good morning. I have a method for solving linear equations that you might find handy. You see here two equations with variables t1 and t2. t1 and t2. The reason these are called linear equations is that they are actually equations for lines. If t1 and t2 were plotted on a graph, the first equation would represent one line and the other equation would represent another line. As a matter of fact, let me show you that in a Mathematica. We have this equation here, 100 minus t1 sine 37 degrees minus t2 sine 53 degrees is equal to 0. And we also have a line representing t2 cosine 53 degrees minus t1 cosine 37 degrees is equal to 0. You can see that there is one combination of t1 and t2 that meets the criteria, and it is right around. t1 is about 62, and t2 is around 79.9. This concept can be extended to more than two dimensions. For instance, 3x plus 2y plus 5z equals 50 gives an equation for a plane in three-dimensional space. If I show that plane with another plane, 2x plus 5y plus 3z equals 50, you can see that these two planes intersect in a line. But with three unknowns, we need three equations to explicitly find our answer. So I'll throw in 5x plus 3y plus 2z, and that will narrow our solution down to a single point right there. Okay, I got a little bit sidetracked. My intention was to show how to use linear algebra in a scientific calculator to solve these sets of linear equations. So the first key to doing this is to rewrite so that the constants are on the right and the unknowns are presented in the same order in each equation on the left. You see up here we've got the constant 100 over on the left. We've moved that 100 over to the right and then made sure that the t1 and t2 are on the left-hand side, t1 and t2. Same thing with the second equation. There was no constant, it's just 0, so that 0 came down. But then we made sure that the so that the t1 and the t2 were in the same order as the other equation. So t1, t1, t2, t2. The next step is to convert the two equations into a matrix multiplication. I don't know if I have time to explain exactly what matrix multiplication does, but suffice it to say, you want to put your unknowns in parentheses like this, t1 and then t2, and the coefficients over here to the left, the sine 37, sine 53 goes sine 37, sine 53, and negative cosine 37 and cosine 53 goes negative cosine 37 and cosine 53 in the same order that they appeared above. Then bring your constants down, the 100 and the 0, stacked on top of each other in parentheses 2. Now the cool thing about matrix multiplication is that it's sort of like scalar multiplication. It has an inverse function, but it has a peculiarity. So if I were going to solve this equation up top, if I were to solve the above equation for x, I could just do the following. I can divide both sides by a, and I will have x equals b over a. But matrix multiplication has a peculiarity. Unlike regular multiplication, matrix multiplication is not commutative. So I can't simply say ax divided by a equals b divided by a, because in fact that's not even possible. But I don't think I'm going to explain exactly why right now. I'm just going to show you the way So instead of showing you why that's not possible right now, I'll just show you the way that works for both regular multiplication and matrix multiplication. So in regular multiplication, I can go ax equals b, and then multiply both sides by a inverse. So this would be 1 over a. X equals a inverse b. And this works because I'm not using the commutative property. I'm just putting this before the thing in both of them. Now a inverse times a is 1. So 1x equals 1. This would be 1 over a times b. So this will work with matrix multiplications. I can say x equals a inverse times b. So if I can find the inverse matrix of something, then I can find out what the solution is. So here I have my matrix multiplication. I'm going to call the matrix on the left matrix A, and the matrix on the right matrix B, and then the matrix, what I'm going to solve for is the central matrix, matrix X, or matrix T1, comma T2. So what I will do is I'll plug A into my calculator, and I'll plug B into my calculator, and then I will find T1 and T2 will be equal to A inverse B. And I'm going to attempt to do this with 3 different platforms. The TI-83, the TI Inspire, and Mathematica. We turn on the calculator and make sure that it is in degree mode. Second, I will define my matrix by going to second matrix. Where's the button? Oh, I won't use second. I'll just hit the matrix button. Go over to edit and choose A. Tell it that I want this to be a 2 by 2 matrix, and then start entering my values, which I didn't have to calculate ahead of time. I can go sine 37, 37, parentheses, enter, and then sine 53, enter, cosine 37, enter, and cosine 53. Next, I want to enter the values for matrix B. Again, matrix, edit, this time matrix B. I want a 2 by 1 matrix this time, and I will enter the numbers 100 and 0. Now I'll go back to the calculator mode and just type in matrix A inverse times matrix B. Enter. And simple as that. Or I should say, simple as that if these were the correct answers. I see what went wrong. My calculator was blocking a vital piece of information on the screen. So this negative cosine 37 should go in. There should be a negative sign in column 1, row 2 of matrix A. So I will go back into matrix A and change that so that it is negative cosine of 37. And now go back, second quit, and do matrix A inverse matrix B, and we'll have 60.2 and 79.9. We now have a correct result of T1 equals 60.2 and, or 79.9, so we can say that T1 equals 60.2 and T2 is 79.9. I was planning to show how to do the same thing with the TI Inspire, however it appears that my emulator needs to be reinstalled. There's a missing DLL. So I'll skip the TI Inspire and go straight to the Mathematica version. In Mathematica, matrices can be entered very simply using that kind of construction. So I'm going to enter that, comma, no, just that. Okay. And then by default, the trigonometry is all done in radians, so I'm going to use a factor, degree equals pi over 180. So that is, so anyway, this is going to be sine of 37 degree, comma, sine of 53 degree, and negative cosine of 37 degree, and comma, cosine of 53 degree. And let's see how that comes out. It's not calculating it. Let me put a decimal in here. A lot of times if you put in a decimal, it gives you an actual number. And then, okay, now it comes out. And I can see that in matrix form, but I'm going to define that as A equals that, and B equals, I think I can just do this one like this, 100 comma 0. And then I just say A inverse A dot B, and it gives us those two numbers. So in Mathematica, you need to use this inverse function instead of the -1 that you would use on the TI-83. You'll notice that when I plugged in to the -1 power, it actually gave me each element to the -1 power inside the matrix. So, also Mathematica uses a period to represent matrix multiplication. Okay, let's also explore a little the matrix form function in Mathematica. It shows you better what are the rows and columns. For instance, if we try matrix form, whoops, this matrix form, whoops, what did we get? Nothing. We need brackets around it. Get A, B, C, D. What about this one? Let's put brackets around it before we do it. I'm guessing that's going to be right next to each other. No, it wasn't. How about this one? How would I get two of them right next to each other? Let's go matrix form. A comma B like this. And that would give us a horizontal probably. Yeah, that gave us horizontal. Okay, let's do one more thing before I go. Earlier I had 3 equations and for planes, and let's put these 3 equations together in the form of a matrix multiplication and solve them for the point of intersection. Again, this is going to be a 3 by 3 with the x, y, z down the side over here. and it'll be 325, 325, it'll be 253, and 532. And we can just say A equals 3, 2, 5, 2, 5, 3, and 5, 3, 2. And let's see matrix form of A. And it's all lined up like that. And so B equals 50, 50, 50. And let's see the matrix form of B. Also 50, 50, 50. All right, now let's take inverse of A dot B. That gave us 5, 5, 5. Does that look accurate? Whoops, I need to go back into Mathematica and find that. Okay, so if it is at 5, 5, 5, it should be at the very center of this block because it goes from 0 to 10 in each direction. And I would say yes, it does appear to be right at the center of that block. Okay. In summary, this is the basic idea. When you have any number of linear equations and the same number of unknowns, you can always group them together in the form of a matrix multiplication. If you can figure out how to enter the matrices into the calculator or software, and then figure out how to get the inverse of the matrix, you can get all of the solutions in one more step by taking A inverse times B. So I hope you've enjoyed this video on how to solve linear systems of equations using the TI-83 or Mathematica. Thanks for watching.